Welcome to vgac, calibration-aware GPU queue intelligence. vgac tells ML teams why their GPU jobs are stuck, and when they'll actually run. 150 API endpoints, 12 dashboard pages, 5 autonomous agents. Let's take a look. GPU clusters are the most expensive infrastructure in AI, yet scheduling is still a black box. Researchers submit jobs and wait, sometimes minutes, sometimes hours, with zero visibility. A 100 GPU cluster costs $2.6 million per year. 15 to 25% is wasted on scheduling inefficiency. That's up to $650,000 in annual waste per cluster. vgac is a full-stack observability and intelligence platform that makes GPU scheduling transparent, predictable, and self-improving. Let me walk you through the dashboard. The overview dashboard shows real-time platform health at a glance. Prediction SLI shows 100% uptime with a 99.9% success rate. Over 6,000 predictions have been served with 98.7% accuracy. Below we see GPU allocation breakdown, model health status, request rate trends over time, top error patterns, and service health for all backend components, ClickHouse, Redis, and the API. The queue page reveals scheduling pressure in real time. 4,962 pending jobs. 91-second median wait. We show GPU block rate, queue pressure index, and job distribution by namespace and GPU request count. The Wait Times tab provides a histogram of wait time distribution across time buckets, under 1 minute, 1 to 5 minutes, 5 to 15, and so on, with percentile breakdowns for P50 through P99, plus built-in slow monitoring. Per GPU monitoring shows utilization heat maps, red, yellow, green per GPU, along with temperature readings and detailed utilization and memory bar charts across all GPUs in the cluster. The GPU capacity view shows overall cluster health at 68.8% utilization, wait time by GPU class, and per GPU telemetry tiles with temperature indicators and health scoring. The prediction SLI page tracks model performance in production. 3,627 predictions served with 5.5 millisecond average latency. Our model achieves an OROC of 0.969 and an ECE of 0.005, meaning our probabilities are accurate to within 0.5%. This is the core user experience. A researcher configures their job, GPUs, CPU, memory, partition, and clicks analyze. vgac returns a wait time estimate with reliability rating, placement alternatives across namespaces and GPU counts, a visual GPU allocation map, and a lint score with warnings about resource configuration. The cluster page shows capacity forecasting, current utilization at 63%. Predicted to reach 66% in 1 hour and 71% in 4 hours, plus a per-node GPU utilization chart and detailed node inventory table. vgac's AI pattern engine detects 4 recurring patterns and generates 3 predictive alerts, like GPU contention expected in the next 2 hours and potential out-of-memory risk on node B1I2. Each pattern includes severity scoring, frequency, and confidence scores. Purpose-built for LLM serving workloads. The inference analytics page shows phase bottleneck distribution, 412 prefill bound, 687 decode bound, 535 balanced. KV cache health gauges show 73% hit rate and 18% fragmentation, plus a 127 millisecond potential improvement through disaggregation. Below, we see actionable insights, like 34% phase imbalance detected, enable disaggregated serving, per model efficiency comparison for Llama 370B, Mixtral 8x7B, and Code Llama 30, 4B plus cache optimization recommendations. NVIDIA NIXL transfer monitoring shows 5 active agents, 2 backends, UCX and TCP, 3.4 millisecond average latency, and 42.7 gigabytes per second bandwidth. The scaling decision engine and backend recommendation system help optimize cross-node transfers. The HPC page provides Slurm native features, request linting, job feasibility analysis, topology health checking, and GPU accounting status. VGAC can even generate optimized Slurm submission scripts based on current cluster state. Under the hood, VGAC runs as two independent tiers on AWS. The platform tier on ECS Fargate handles observability, Fast API, ClickHouse, Redis, and Next.js. The agentic tier is fully serverless, Lambda functions, DynamoDB, API gateway, and Bedrock for the Copilot. The key innovation is calibration-gated autonomy. 5 agents: observer, predictor, calibrator, actor, and copilot gate every autonomous decision on the model's calibration score. Above 0.85, the agent acts on its own. Between 0.6 and 0.85, it recommends to a human. Below 0.6, it escalates. The system is self-aware about its own reliability. That's VGAC, Calibration-Aware GPU Q Intelligence. Open source on GitHub. Built by Andrew Espira, Team vgac. Thank you for watching.